What's something about Trimble engineering that maybe is a great strength that most people don't know?
Yeah, so I think from the GNSS, GNSS or GNSS Plus, I think it's the level of testing that's going on here. So I always, when I'm presenting on this, I always kind of show a slide of an iceberg, and you've got the top of the iceberg. That's kind of what the customer sees, and there's all this work. There's what 2/3 of the icebergs under the surface, or maybe more.
In this episode of the Point Taken podcast, we sit down with Stuart Riley, the Vice President of GNSS Technology at Trimble. Stuart manages engineering teams across Trimble, including in the Sunnyvale, California office, where he's based and where Trimble got its start, as well as other locations, including our Terrasat office based in Munich. In this episode, he gives his current state of GNSS overview, which looks at the current state of GNSS systems, what's coming up, what's new. He also talks a lot about Trimble's approach to GNSS engineering and product development. He talks about some of the testing that our GNSS systems go through, both on the hardware side and the signal processing side. If you use survey grade or commercial GNSS systems, we think you'll get a lot out of this episode and learn a little bit more about how Trimble approaches GNSS. When you've talked at a lot of our Trimble Dimensions conferences and other talks, you kind of give a current state of GNSS, which I think is interesting, looking at some of the new signals that are coming out, some of the work I think you're doing with different government organizations. Can you talk a little bit about what's the current state of GNSS?
So, we have 4 primary signals today, or primary systems, that are global. We have GPS, GLONASS, Galileo, and Beidou. So they're available worldwide 24/7, and all of our products have them. Then you have a couple of regional systems. So in Japan, you have QZSS that you do receive it outside of Japan, but it's essentially focused on Japan. So you'll see it in Eastern Asia. You'll see it in New Zealand, Australia, and even on the west coast here, you do see the satellites, but not at a very high elevation. So there's that regional system, and they are adding more satellites. There's Navic in India, which used to be called IRNSS, that rebranded it a few years ago. That's a growing constellation. They're changing some of the signals there, so that's being enhanced as well. So they're the ones that exist today. The really interesting thing right now is private constellations. So all of those are government run. All of them are free to use. But now we're seeing a few companies that are putting satellites up are going to run a commercial GNSS. So one we've partnered with, this is public, we've announced an investment and partnership with them, and just a few weeks ago we announced that we're actually tracking their satellite. So they launched a satellite, I think it was a little over a month ago now, their first satellite with their commercial signal, their default signal, and that's live in space. We are tracking it as I said, and they're planning to put 250 plus satellites in space.
Oh, wow. Will those orbit a similar orbit as?
That's a very interesting point. So all the other systems are in what we call medium Earth orbit, or geostationary Earth orbit. So they're relatively high above the Earth. Now it's expensive to get the satellites up to that height. They're big. You need a lot of fuel. It's very expensive to get them there. What these new systems are planning is low Earth orbit. So this is orbits a little bit higher than Starlink, than where the space station is. They're planning that orbit. That's much cheaper to get into that orbit. For example, the current satellite, the test satellite, went up on SpaceX's Transporter 14, and I think there were 50 or 60 other satellites. So they shared the cost for that. So it's much cheaper than putting into GEO or MEO. So the downside is, because it's much closer to the Earth, it doesn't light up as much of the Earth. as a MEO
Less
or a
coverage.
GEO, just less coverage
Okay,
per satellite. And so that's the downside. That means you need more satellites. Now the upside is because it's closer to the Earth, there's less loss in signal before it gets to the user, so you can have higher power signals, which have benefits for anti-jam, for anti-spoof, and also just to penetrate things like buildings, trees, etc. So we are seeing that the Zona signal is much more powerful than GPS, for example.
Okay. In terms of just distance in miles, the Zona satellite versus a GPS, what are the ballpark?
I can give you kilometers. So
kilometers is fine. Yeah.
So the Zona, or the test satellite's a little over 500 kilometers.
Okay.
The final satellites are going to be more like 1,000 kilometers.
Okay.
GPS is about 20,000 kilometers. So
Wow,
about
so that's
20x.
like significant.
Yeah.
Change in distance. So okay. Yeah, tell me about maybe a really interesting story you've had at Trimble, or an interesting milestone you feel like Trimble has gone through. So
I think one milestone is when I joined Trimble, we were a GPS company. We were not a GNSS company. So for many years we were building just GPS receivers, L1 and L2. We had looked at GLONASS. GLONASS had been a live system for some years. We built a couple of prototype receivers, one before I joined, one after I joined, but we never productized it. We took the decision in I think it was the late 90s, to actually go ahead and add GLONASS. So technically not a massive lift because it's quite similar to GPS, but it really did set us up and had a sort of inflection in our thinking, because we went from a GPS company to a GNSS company in our products, and then from that we added Galileo, we added Beidou, we added QZSS, Navic, and now Zona. If we'd have stuck much longer to GPS, we would have lost relevance, because a lot of our competitors were either already put GLONASS in the market or already or soon did put GLONASS into the market. So I think that inflection was very important to Trimble.
You almost look at that period before and then that period after. So with our current GNSS engine, which we call ProPoint publicly, that I've heard is GNSS agnostic. So whereas our old engine in, say, the R10 or something could only, like, it had to have GPS and then it would kind of add signals on, or is that not true?
It's not quite. So our very old engine, but I think our prior generation to ProPoint didn't need GPS. It might have done early on, but we did have the capability to be agnostic to GPS. But it was a lot more restrictive. It needed L1 CA code, for example. It was very restrictive in the signals that it needed. ProPoint is very signal agnostic now. So if L1 CA code from GPS is jammed, it can still use L2C and or L5 from GPS. So you can mix and match those signals. Now, it's a little bit degraded. There's a reason we use all of these signals.
Right.
But it will still give a pretty good solution, even with some of the signals missing.
And you could run a GLONASS only solution.
Yeah, you can run a GLONASS. You can run a GLONASS only solution. Of course, it won't be anywhere near as good. With the added satellites, we do see a significant performance benefit. In the middle of an open field, maybe the difference wouldn't be that much, but many of our users are not in the middle of an open field. So as you start to get some obstructions, you really do see the benefit of having that quad system.
Okay. Yeah, and is with the mixing of signals, being able to pull from different ones to get a solution, is it actually happening within the constellations? I think I had a very odd case of, like, if you had one GPS, one GLONASS, one Beidou, like, could you actually form a solution?
Well, you do have a couple of problems, because each system's on a different clock, so you need to account for that. So you can't
need
just
a minimum number.
So you need a minimum number for that. But then once you get past that threshold, then basically we don't care what's there.
Talking about different constellations, you've also used this term GNSS Plus, which is even more than GNSS. Can you talk a little bit about what you mean by that?
Yeah, so if you look at the history of Trimble, we're GPS only, then GNSS, and then probably 20 years ago that we bought Aplanix, and so we started to think about different sensors, and we'd use them also in ag, maybe even before that time. So to me, when I say GNSS plus, I mean the satellite signals, but all other sensors beyond that. So the first set of sensors are IMUs, but then there's video, there's other sensors that we're integrating into systems.
Would you say, is that something that your team is constantly evaluating, this sensor fusion?
So I have a technology team. It's based in Munich that are looking at sensor integration. So they're scanning what sensors are out there and how they would integrate that into the ProPoint engine. And then you've got the marketing team that are trying to decide, well, what do we want in a product? What are we trying to do? And then bring those teams together to try and figure out where's the reality. Yeah. So you might have a desire to do something, but it might cost far more than the market could be.
Right.
So we bring those teams together to understand what we can actually develop within the time frame.
Yeah. And then but then a lot of times it might be the technology team is working with different sensors and discovers, hey, this is actually maybe a better solution or a better asset. Do you want this in the next product?
I mean, I'll give you an example. There's the R12 I and the tilt compensation.
Right.
So that's something that we'd been looking at for many years and just didn't quite get it ready in the R10. So that had some lower performing tilt compensation.
Yeah, it had a basic version.
Yeah, but it wasn't anywhere near as good as what we got to into the R12 I. So the team were in the background looking at different sensors, looking at different algorithms. We had the transition from the legacy PVT engine to ProPoint there as well, and all those pieces coming together allowed us to enable that tilt compensation for the R12i.
Yeah. Can you tell us about this office that we're in, which we call it the Sunnyvale office? Was it the original Trimble office here? Or?
Well, so Trimble was in the Bay Area originally, but not on this site.
Okay.
So there have been different sites before I joined Trimble, but probably 20 years ago, we moved to this site. We've had different building configurations, but we just renovated this about 2 years ago. So this is our latest instance here.
A lot of tradition, a lot of history here.
Sure. And that's before the Westminster office. So when that was founded, some people from Sunnyvale did move to Westminster and then grew that office.
Okay. Yeah. Is it still, you think, advantageous having this location here? Is it kind of in the heart of a lot of software engineering?
I mean, you obviously you have access to talent here, and so you also have other GNSS companies. You have other things going on in the Bay Area, so it's useful to be here. So I think it's good that we have a site here. Obviously, we have Westminster as well in the US. We have the Munich team, which is part of my overall group, and then we have some other offices with people elsewhere.
But can you talk us through some of the things you showed us this morning of the testing labs? And
sure. So, we're responsible here for developing the hardware, but also ensuring that when you receive the hardware, not only does it work on day one, but it works several years later. So downstairs we have, starting with temperature testing. So we have chambers that can ramp up and down temperatures, can stay at cold, stay at hot, and there we're looking for problems in extremes of environment, or when you see temperature ramps, when things ramp up. We have a vibration test system, so you need to make sure from just the simple things where it goes through shipping to make sure that it gets to the customer, but also if you're putting on a bulldozer or a tractor or even just man-portable, is it going to survive? Is it still going to work after a few years of that environment? So we can stress it there. We've got anechoic chambers and screen rooms for making precise RF measurements. We have labs full of just receivers that are operating 24/7, that are Some of them are connected to just live sky antennas on the roof that are just making a set of measurements to just do some quality checks on the performance. We have receivers that are connected to simulators doing similar things but with more perfect signals. We have labs where we are now spoofing and jamming the GNSS receivers to see how they react to that. We have just more specialized equipment like UV testers just to make sure that materials aren't decoloring and degrading after exposure to the environment. I think that covers most of what we have here.
Yeah. And you even showed me some rooms where you can isolate signals like.
Yeah, so we have the screen room, so that's essentially a Faraday cage, a metal box, so you can put equipment in there, and if you're doing some measurements to look at emissions, you can be sure that it's the equipment that you have in there that's emitting and not something externally. And you can do things in there that you couldn't do externally. You can transmit in there without it being illegal because you're in that screened room. We also have an anechoic chamber where you can again look at antenna patterns and make other precise measurements without the signal bouncing around because it gets attenuated by the walls there.
One question on that vibration table or vibration machine, is it more about just reaching an intensity of vibration, or like what's the longest it would be on that table?
This can be on there many hours. It's not just so you want to look at you're essentially trying to accelerate the testing. So rather than put it on a bulldozer and drive around for days or weeks, you want to try and do something more intense. So it's both the displacement, but also the frequency. So you might find you have a resonance. So you're going to put in energy at different frequencies. So you might find that the wheels rotate at a certain frequency, and that is the bulk of the energy that you get in a product. So we have different profiles with different energies at different frequencies where we can sweep through, or we can do random patterns to look at how the product reacts to make sure that we don't put on a machine with a certain vibration characteristic and it has a problem.
Yeah, you can isolate those and test them. So that's interesting. So a lot of the test is meant to speed up. A few hours on a machine could be weeks, months in real life. So, okay, that makes sense. So you mentioned doing some testing here for jamming and spoofing with our products. Are you seeing those as real threats with our users getting jammed or spoofed?
Yeah, we are. So it's jamming's been a threat for a long time, but it's been more very localized pockets of jamming. So you might occasionally see during one of our tests where you'd have a problem, and when we look dig into the data, there was some brief jamming. And either two classes, and from that perspective, faulty equipment, or somebody maybe not understanding what the implications of jamming are. So they're illegal, but there are some devices you can buy that plug into a cigarette adapter on a car, and they will jam the GNSS. So you can imagine a worker has a GPS tracker, a GNSS tracker, and doesn't want his employer to know where he is.
Yeah,
what
hey
he's
boss,
doing.
don't know.
So they put a jammer on, and there was a case probably 15 years ago where a trucker was doing this by New Jersey airport and taking out GPS for the airport. Every few days they were driving by, and eventually the FAA figured out, using some video, and figured out what was going on, and he got fined quite a lot of money. So we see those kind of things. Spoofing was largely an academic exercise, but all that changed a few years ago. So
it used to be pretty sophisticated to spoof something?
It's much harder to spoof, but it's getting easier. Yeah, so it was hard. I would say it's not hard now for one skilled in the art. But things change with the growth of drones and the conflicts that we see. So as you know, there are conflicts in various places of the world, and a lot of the modern warfare is using these cheap few $100 drones to deliver some level of munitions. Now they need some form of positioning, and so many of them using GNSS. So there's a lot of military state-sponsored jamming to at least have one level of defense against those. So we see around the Baltic, around the Black Sea, we see around Israel. We see all these areas are very hot spots for jamming. Now, our customers are developing or using GNSS for just regular civilian application, farming, construction, survey. But these jam signals don't respect national boundaries. So you may be jamming around Israel, you may be jamming in Ukraine, or Russia may be jamming to prevent Ukraine munitions getting into their territory. Yet those signals can travel very large distances. So we see on the coast of Romania, on the coast of Bulgaria, we have some customers working there. We see effects, and it's coming from that conflict region. So and we see a combination of jamming. So jamming is really a denial of service. So you try and overpower the receiver so that it just stops positioning or receiving GNSS signals. And then spoofing is really a sort of hazardous, misleading information that you're trying to provide. So what you're trying to do is you're trying to get the GNSS receiver to track a spoofed signal, so a signal that you create, and from that derive a position that you essentially send to the receiver, fundamentally. And so what you might be doing is a lot of drones are supposed to have within their software, if they go into an airport airspace, they're supposed to ground the drone. So if you can get the drone to think it's in an airport, then it should just land or go back to where it started. So we see spoofing as a secondary deterrent, and again, that's impacting our customers. It's also impacting aviation. We're not really in aviation. We're not developing safety of life systems. We are in photogrammetry on planes, but we do see a lot of commercial planes are affected in these regions. They're not flying over Ukraine, but they're flying a few hundred kilometers and can still get affected by these signals. Okay.
So talk to me about what Trimble can do to help prevent that, because with jamming, if it's just loss of signal, it's just washed out, how do you actually do anything to help recover from that? Or
well, so there are things you can do. So there are some future looking things that we'll have to edit out. You typically are not jamming every single signal. It's kind of an arms race. It's a power sophistication range. So we track L1, L2, L5, E6. We track a lot of different frequencies. So we've got this frequency diversity. So we are making our system much more signal agnostic. It's not completely signal agnostic today, but it is becoming more agnostic. So if L1's jammed, if L2's jammed, we can go all the way down to an L5 system. So it just raises the bar at what the hostile jamming source has to do. And
that's built into ProPoint already, that your receiver will perform better.
That's right.
With jamming some of the older ones.
So we're already doing much of that. We on spoofing. You typically won't have every single signal spoofed. You certainly could. So there we're doing what we call a Swiss cheese approach to it. So we're applying lots of different methods to try and look for spoofers. So for example, a very simplistic attack may be just on GPS L1. So if we get spoofed on L1, the L1 would give a different position to Galileo, to Beidou, etc. So when we start to see inconsistencies, we'll start doing inter-system tests. So is Galileo consistent with GPS? Is GPS consistent with Beidou? So we can do all of this cross-checking. Is L1 consistent with L2C or with L5? So we do those kind of cross systems. There are some signatures in the RF, so you can see different patterns on the signal to noise ratio or in the spectrum. So we're looking at those to see is there some anomaly and can we try and detect it? And then ultimately, if we have been spoofed, can we determine where the legitimate signal is, and actually then transition back to that.
Yeah. Okay. And does that happen just behind the scenes?
Yeah,
So
it's all behind the scenes.
you figure out how to do that.
Yeah.
It goes in the firmware, and then it's just part of that.
Yeah, so we have a whole bunch of statistical tests. So we run some basic tests all the time.
Okay.
And then when we start to see anomalies, a lot more things kick in under the hood. You just don't see it.
Yeah. So it's
Yeah.
working, and you don't even know that it's.
Yeah,
to sort through that.
and then the systems are starting to put some protection in as well. So Galileo has had this system they called OSNMA, Open Service Navigation Message Authentication. So that's been live for a year or two in a test phase. It just went to an official operational phase just a few weeks ago.
Okay.
And what that does is all of these GNSS systems are really fundamentally go back to GPS, which was designed in the 70s. And so the level of encryption and trust is there's really negligible extra controls on top of it. So it's kind of like Wi-Fi with no password, or just sending a postcard through the mail. Everything's there. It could be intercepted, could be tampered, could be passed on. So for Galileo, what they've done is they have everything open, so you can receive it, which means you can generate something that's illegitimate and would actually spoof it. But what they also do is they put this what's called a hash, so basically a little code on top of the data using private keys, which when you receive it using an appropriate algorithm, you can see whether the data is legitimate or not. And so they don't make that private key public, so somebody could try and put these hashes out, but they wouldn't match because the keys wouldn't match. And so then you can tell that the data has been tampered and is not that legitimate. So and then what we've done, and this maybe isn't widely known, is RTX is a paid for service for precision positioning, but we've added a free layer. This has gone live about 6 months ago. And we've added what we call NMA, Navigation Message Authentication, for GPS and for Beidou. So if you have a Trimble receiver and you track our beam, our RTX beam, or you get the corrections off the internet, even if you don't have an RTX subscription, we send these little hashes for GPS and for Beidou, and we're protecting the user. So we can then now do authentication on both GPS and Beidou from our system, and then we'll layer OSNMA. So we've got three systems that are protected. It's not completely foolproof. There are ways you can get around that, but it's this Swiss cheese approach where you're adding extra layers of protection to the system. So that's
interesting. And is that something that just needs to be enabled in the receiver?
You need one of our modern receivers, so one of our modern ProPoint receivers. You need fairly recent firmware, and you need to be tracking the MSS beam, which is how we get the RTX corrections, or using the N-trip connection. You don't need a subscription.
Kind of leads into a side question about RTK I've been wanting to ask for a while. Yeah. When I first learned about GPS and GNSS, there was this idea of RTK fixed, and it would even show up on the receiver, and it was, you probably get these dopamine hit of like, yes, I'm RTX fixed, especially when there weren't as many satellites. Now, has that changed in terms of how the GNSS engine works? Is it that does it suddenly snap into this position, or is it kind of different on how
it's somewhat of a continuum? So we like to think more of a statistical threshold now. So you will dial in, I want a 4 centimeter solution, or I want a 2 centimeter solution, or a 10 centimeter precision. Setting your precision, and so from there, we don't need the customer to be too concerned about what we're doing under the hood. Just set that precision, and then we'll deliver a position to that position if we can, or if we can't, then you know not to store that point.
Okay. So is it, I don't know if that really, it answers it practically, but is it, we actually kind of, is it working different than it used to?
Yeah, so definitely there are some differences under the hood that were part of the, certainly in ProPoint, a little bit of the technology was in the previous engine, but in ProPoint, there is a difference to how that is done.
But a user might see the precisions converge
at
a more regular stream.
But there still will be some snapping. You will still see some dramatic changes as we converge.
Okay, interesting. Yeah, I think people really like the RTK fixed, and it's, but I think more practically now it's just, is your precision met is really the thing you want people to understand about it. So what's something about Trimble engineering that maybe is a great strength that most people don't know? Is there anything you can think of?
Oh, you stunned me here.
Something we don't talk about much maybe, but you feel like is a great strength with the engineering we do at Trimble.
Yeah, so I think from the GNSS, GNSS or GNSS Plus, I think it's the level of testing that's going on here. So I always, when I'm presenting on this, I always kind of show a slide of an iceberg, and you've got the top of the iceberg. That's kind of what the customer sees, and there's all this work. There's what 2/3 of the icebergs under the surface, or maybe more, and all of this work is going on under the hood. So we have just an enormous number of test systems. I mentioned a few things, touched on them earlier, but we've got a bank of receivers downstairs that run 24/7. We have a whole bunch of scripts that kick in and look at the measurement noise, look for outliers, look for cycle slips. We trend this so we can see has something changed. When we put new firmware out, has something changed? We'll look at the multipath on that. So has the multipath estimate change? So sometimes we expect it to get better. We make positive change. Occasionally, yes, we have a negative change we didn't expect. We introduce a bug. So we want to find all of those things before it gets to the customer. So that's just one test system. We have an RTK test system where we've got probably thousands of hours of data, maybe tens of thousands now, where we've captured data at various places, customer problems, data that we've gathered. And whenever we implement a change, we will run through a subset and then ultimately the full data set to look for how things changed.
Cycle through a test.
So when a T02 or T04 is really the input to the RTK engine. So we have a PC engine of ProPoint, and we can actually run that through the data. We can just run it continuously, meaning we just let it fixed and just look at what the performance is through that data set. Or we can actually stop it and every, say, 10 seconds and get it to do an initialization, as though the receiver was turned on at every 10 seconds. And so we can look at the performance and look for outliers, and effectively we're looking for change. Did it get worse and unexpected worse, or did the changes that the engineers are making make it better? So that's just a couple of things we have. We have similar systems for jamming. We have something like 50 different jam scenarios that we run through to see how the system performs. And then we have hardware in the loop testing that we've been doing for maybe 6 or 7 years now. Where I talked about the T02, T04 files. That's the input to the RTK engine. It's the output of the signal processing. So before the RTK engine, we need to go from essentially that signal that hits the antenna to measurements, and that's what the signal processing layer does.
Right.
So now to test that, historically we'd just have it running in live sky. We'd use a simulator, but now what we've done is we've recorded basically the output of an antenna. So there are devices where you plug in a GNSS antenna, and it will digitize that signal, and then you can play it back in the lab. I like to think of you essentially bringing that environment into the lab. So what you can do is you can go do a drive test. You can drive around and under overpasses, around buildings, around trees, and then you can get creative, and you can start to map out, well, where are all the overpasses? And so and then you can look at the tracking as you get close to the overpass, and under the overpass you can find out where all the trees are. But because you've captured that signal, you can replay that over and over again. And so then you can look at how, again, the trend changes with time. So did you make an algorithmic change? Did it make it worse? Did it make it better?
Right. And
you can actually look at that full system. And you can go, because this is the signal at the input to the antenna, we can do the whole receiver chain all the way through to the RTK or the RTX engine. We just need to log the corrections at the same time, and in fact we can even log IMU data at the same time and replay that all back. And so we have a system that automates that testing. Every weekend we do about 60 hours of driving. No one has to get in a van and do any driving, but it's just going through all of these data sets, and then just puts extra points on a trend plot, and we can see whether something improved or degraded. And we have data from from here, from Germany. We have from some tests, some special tests we've done in tough environments, in easy environments, and we can look at how that changes. So that saves. When we develop a new receiver now, we can do a massive amount of testing before we even need to get into the van or have a person go out and do some survey work. We've got all of that data that we can actually just have it automated in the lab here.
Yeah, I'd say there's a huge strength. There's almost a library of data sets, conditions, things that we've built up over time in-house that we can test and make sure our equipment's better, our products are better. Whereas if you started today, you could build a GNSS product, but you wouldn't have that legacy.
Yeah, it just takes a long time to build that up. So for example, scintillation was a big thing. Last year into this year.
Right.
I mean, it's less of an issue for Trimble given we've got Eye on Guard out now. But we, as we were building that system, we managed to capture some of these events and then able to use that the signal processing layer to ensure that that's operating most effectively, and then we can keep replaying that through the system.
Yeah. Okay. Since we're kind of on GNSS engine processing, I was talking with Eric earlier, and he mentioned the Stinger engine, and I wasn't sure what that was because normally we talk about this GNSS engine that's ProPoint, but he mentioned that there's another engine. Can you talk to us about what the Stinger engine is?
Sure. Yeah. So that's the tracking or the digital signal processing (DSP) engine. So essentially, in our system, we have a digital chip called Maxwell. It's essentially a dumb chip, so it's really hardware acceleration. So it has a lot of hardware that will run in parallel to speed up the processing. You could do all in software, but you would need a very fast CPU, GPU to do that.
Okay.
And so it wouldn't drive the power, size, cost. So that chip does that signal processing, but it needs a control layer to control it because it's done. Yeah. So it needs something to actually run the filters to extract the measurements. So essentially what we have is into that chip is the digitized set of signals. So you take L1, you digitize it, take L2, you digitize it, and that goes into that Maxwell chip. And Sting is that control layer that basically takes the output of that chip, runs some mathematical algorithms, and then applies different parameters to track the signals fundamentally.
Okay.
And then also within that system, it does things such as extract the measurements, so the pseudorange, the phase, the Doppler. It extracts all of those parameters, putting it into SI units, into meters or hertz, etc. Something that the ProPoint engine can then consume. The other thing it does are things like the NMA stuff that we talked before. It's done in that layer, extracting the data. So all of the satellites transmit what we call ephemeris data. This is a low rate set of data that gives us the parameters so we can calculate where the satellite is in space. And so it extracts all of that data, putting it into a nice structure that other systems within the subsystems can consume. Okay. It has algorithms within that, don't necessarily need to be in that module, but they are for doing the satellite position calculation, so consuming that data and calculating the position. And then it has a bootstrap / backup position engine, so it has a crude position engine.
Okay.
So when we very first start up, that is the very first position engine that will run. You might not get a position, the customer might not see that, but that's the bootstrap engine because this is the very tight control of those channels. You need time, you need other things. So we have a small PVT engine there.
Yeah, that's interesting.
It's ultimately a backup engine. So if Titan, in an extremely harsh environment, and not able to deliver, usually that engine can deliver, and so it will deliver a much lower precision, meter level, maybe more, but can deliver a position.
Yeah, that's interesting. Yeah, and it's not like that's a secret name, but it's also not like a public name. It's just what your team refers to as
it's a name. It's a name that was actually created before I joined the company, and we've not been original enough.
You don't know.
So the team. So prior to me joining the company, we had Maxwell, but then we also made a cut down Maxwell called Scorpion that was for the automotive and other markets. It was L1 only, and it had basically a cut down Maxwell and a CPU, and then Stinger was the software that enabled Scorpion.
Give it the punch. Yeah. We actually have I think one of these Maxwell chips. I don't know if the camera can see it, but I mean, is this really the heart of a
so basically, if you've got the antenna, of course, on the back of the antenna you have an LNA, a low noise amplifier, which basically amplifies and filters, and that's the first line of defense from jamming as well. That drops into a companion chip, I don't know if one here, called Polaris, which does the first level of processing, but in the analog domain. And then the output of that is a set of digital samples, and they go into here. This is dumb, it doesn't have a CPU. We pair it with different CPUs depending on the product. So we might put a low-grade CPU on one product or a much higher-grade CPU. So we'll have a CPU and then the RAM and the flash, etc. But this is it. So the GPS subsystem is relatively small. A lot of the size of our products are other things. So, the UHF radio, the power supply. Some of our systems have very sophisticated power supplies. They might want 2, 3, 4 different sources, be it 2 batteries and maybe 2 DC inputs, and so we have the switching logic. Some of them have power over Ethernet. That's pretty big. So we have all of these other things that are on the board that are above and beyond the GNSS itself.
Yeah. Oh, we're proud of the Maxwell chip. It's on that name brand is on our data sheet and something we talk about. But I like Stinger. I like Scorpion. Maybe we should come to you when we trying to name the Trimble products. Get the Trimble Stinger GNSS. I think it sounds kind of interesting. So, is there a path that you would say if you want to get into GNSS engineering, go this path, or is it kind of people come from it?
There are different entry points because when you think about a GNSS receiver, there are very different disciplines that across that product. So you have, if you look at our product, you have mechanical engineers that develop the box. You have RF engineers that develop that front end RF. You have digital engineers that develop that board and the power supply. So basically they're classic mechanical engineering, electrical engineering degrees. Then you have things are a little bit more specialized. So you have the DSP team. They came to Trimble different ways, but electrical engineering, some computer science, some essentially GNSS. Like me, for example, I did a electrical engineering degree, electrical engineering PhD, but during my PhD, my specialism was in GNSS. So you have people that come from that domain. You have people who come from communications, because it is a type of communication system. We're receiving and we're trying to get this timing edge. We're not trying to get high rate data, but it is a communication system. And then on the algorithm side, ProPoint side, then you have people that have skills in estimation theory. So they are developing complex Kalman filters or other type of estimators, and so they have that math, computer science background.
So there's a lot of different ways. There's not you need to do this. There's not really a GNSS degree out there.
There isn't. It'd be hard to cover that. So you have surveying, and you might have so you have surveying. You have other geospatial degrees. So it depends on where you really specialize. But obviously developing something like that, if you want to work on the receiver itself, you're going to need both the math skills, the programming skills, or the hardware skills to be able to develop the product.
To really bring it all in. Yeah. Okay. Can you tell us what's your favorite part about what you do here at Trimble?
I think the variety, So every day's different, It's never dull, I might have a punch list in the morning and hopefully get through some of it. But it's never boring, I don't think I've ever had a day we're on board at Trimble. So there's always a new technical challenge, some good, some bad. But it's just the variety of problems to solve. I like solving problems, and so that to me is the interesting part of the job.
Yeah, that was actually the question I was trying to think of earlier.
Yeah.
You had mentioned that in another interview about you solve problems, and I didn't expect a GNSS engineer to say that. Yeah. But is that really how you view what you do? Is just solving problems?
Yeah, I mean it's so you're trying to make this product better. Yeah. So how are you going to do that? So so to me that's what is the gate? At some point, yes, you cannot make it better. Yeah, the sensors are not going to get better. You're meeting the theoretical limit. But much of what our customers are trying to do is go into more hostile environment, hostile from a GNSS perspective, be it a tree, be it around buildings. And so how do you just pull out as much information of that noise? So to me, that's a problem to be solved. So how much more information? I talked earlier about some of the automated testing. One of the things that we did about 5 or 6 years ago, we were looking at tree performance and how do we get better around trees. And so we have curves where we went out and we got a lot of RF data. We characterized when it was around trees, and so then we could replay this, throw away all the data that's not around the trees, and just produce distributions for that data around trees. And we can look at how, over a course of 6 months, a year, the team were able to actually make that incrementally and materially better by going after and solving that problem. Yeah.
Right. Yeah. So it's I thought it was a great framework that was your mindset and just how your team operates is give us a problem and we'll tackle it.
That's why every engineer likes to solve problems.
Fair.
A technical challenge. How do I make something better?
Yeah, I like it. Well, thank you, Stuart, for joining. I appreciate you being on the podcast and sharing about what you do.